All right, our third lesson on simplifying radicals is actually just using the product rule again, and we're going to simplify radicals that have numbers on the inside, and we're going to look for what we call perfect factors. So we're looking for a perfect square, perfect cube, or perfect fourth, and we're going to simplify those as far as we can. So to show you what I'm talking about here, I want you to, when I mention the perfect squares, perfect cubes, and perfect fourths, take a moment to pause the video and please write these three lists down in your notebook so you have them to refer to. These are the types of numbers that you're going to be looking for as you're trying to simplify radicals. So pause the video and write down these three lists. Thanks for pausing the video. Now let's get to work on this and I'll show you how we deal with this. First of all, just a plain and simple square root here. The square root of 18. 18 is not a perfect square, but we can make this a little bit easier on us and use simpler numbers than this. So what we do is we take a look at the square root of 18 and I ask myself, I'm looking for perfect square factors. So what are the factors of 18? Are any of them perfect squares? When I see one, I think of the factors of 18 being 1 and 18. So the factors of 18 are 1 and 18, 2 and 9, 3 and 6. And what I want to know is, are any of those possibly a perfect square? Since I'm after a square root, I need to look in the perfect square list. And the perfect square I see there is 9. So what I will do then is I'm going to take this square root of 18 and I'm going to use the product rule and I will break it apart, because what that means is the square root of 2, I'm sorry, square root of 9, my fault. I want to start with the perfect square. So the square root of 9 times the square root of 2. So the square root of 18, using the product rule, I'm going to go backwards from what we did in lesson 1, and now I'm going to write this now as the square root of 9 times the square root of 2. I know the square root of 9 to be 3, and then I know the square root of 2 to be irrational because it's not a perfect square, so I have to leave it like that. Now simplified, the square root of 18 is the same thing as 3 times the square root of 2. Considered simpler because I'm using smaller numbers, and the answer to the square root of 2 is much smaller than the square root of 18. So the answer to this being 3 times the square root of 2. Some of you might be wondering, when am I ever going to use this? This is something used in geometry calculations. It is also when we're going to deal with some things with square roots in chapter 8, but you will use this a lot next year in geometry. So we are introducing it to you this year. We want you to get it down so that next year you don't have to have so many questions with it as in high school. So let's look at another example that I have for you. The square root of 44. So again, I'm after a perfect square. So I want a square root, and I'm going to be looking for perfect square factors in 44. Now, I like to sometimes list these out. This could be quite a list. 1 and 44, 2 and 22, 3 isn't a factor, 4 times 11, and then 5 doesn't work because this isn't n in 0 or 5. 6 doesn't work, 7 doesn't work, 8 doesn't work, 9 times 5 is 45, but doesn't work here. So my perfect square factor, the largest perfect square factor I have is 4. So I will now break this apart into the square root of 4 times the square root of 11. And what does that equal? That equals 2, because the square root of 4 is 2, times the square root of 11. And there we have it. And that's it. That is considered to be simplified. I've taken out any perfect square factor. They are on the outside of my radical, being multiplied times whatever is the irrational number that was left behind. Here's a cube root of 40. So now I need to take a look at perfect cubes. So I would then be looking back at this list here in the perfect cube list that I wrote in red. I'm looking for a 1, an 8, a 27, or a 64. Probably not even a 64, but 1, 8, 27. These are all smaller than 40, so I'm probably looking for one of those as a factor. Knowing you, you probably have already noticed that the perfect cube in there is going to be 8. If I list out my factors of 40, I would list them out as 1 and 40, 2 and 20, 3 is not a factor of 40, 4 and 10, 5 and 9, I'm sorry, 5 and 8, 5 and 8. And then that's it for factors. Now I want perfect cubes. I'm not after perfect squares, I'm after perfect cubes. So the number from my perfect cube list that's in my factor list over here happens to be the number 8. So what I will do then is I break apart this using the product rule into two separate factors, and I say the cubed root of 8 times the cubed root of 5. And what does that equal? The cubed root of 8, that happens to be 2. So I say 2 times the cubed root, and that goes on the of 5. So I have 2 on the outside of the radical sign now because the cubed root of 8 is 2. And then that's times the cubed root of 5. Notice I don't put a dot in between. I don't put an X sign in between. Algebraically, we would write just the number next to this radical number. I'll just write the 2 right next to it, almost like it's a variable. I won't even use a dot. I don't use an X. So what happens then when there's variables on the inside? How does that work? We will still use the product rule, and we will still break this apart into separate factors. So I will break this one where it says the square root of 25x to the 5th. I'm going to break it apart into a factor that is the number 25, and then I want to break it into the square root of x to the 5th. Next step, what do I do? I know that the square root of 25 is 5. Now I'm looking for the square root of x to the 5th. X to the 5th is not a perfect square. Your exponent is an odd number. Odd number exponent is not a perfect square. That's odd. So when you have an odd number there, we're going to have to break this apart into two factors before I can go any further. Even number exponents will give us a perfect square because I can divide them by 2. So this is then times the square root of x to the 4th, which is just one less, times the square root of x. So I'm going to break this apart again. I'm going to use the product rule again because I have an odd number here. I have to have an even numbered square root in order to have a perfect square. So now looking at this, I have 5. The square root of x to the 4th, square root, 4 divided by 2 is 2. So that means the square root of x to the 4th is x squared. And then I have a square root of x here that's left behind, so I write then the square root of x. So again, as we simplify, we're looking to pull out as many perfect square factors or perfect cube factors or perfect fourths, whatever we're working with, and we'll write this out here as a rational factor, and then it's times the irrational one. Square root of x stays just like it is. All right. One last example here for you. A cubed root. Cubed root of 24 times a cube, 24, 8 to the 9th, b to the 4th. How are we going to deal with this one? All right, product rule, cube root of 24 times the cube root of 8 to the 9th. Notice I'm separating these, and I deal with one piece at a time. And then the cube root of b to the 4th. Now let's take a look at our factors. Cube root of 24, is 24 a perfect cube? Looking back at my list, no, it's not. In fact, I'm either looking for a 1 or an 8, so I better be looking to see if 8 is a factor of 24, which it is. So I will now rewrite this as the cubed root of 8 times the cubed root of 3, because 8 times 3 is 24. And I've taken care of that right so far. So now I have the cubed root of a to the 9th. So what I want to do is if I want to find, looking here at my exponent, I want to see multiples of 3 because I can do a cubed times a cubed is a to the 6th, and a to the 6th times a cubed is a to the 9th. So I'm looking for multiples of 3 because I'm looking for a cubed root. 9 divided by 3 comes out to a nice integer number. That's 3. So the cubed root of a to the 9th is a cubed because a cubed times a cubed times a cubed, 3 plus 3 plus 3 is a to the 9th. Looking at my last term, the cubed root of b to the 4th. Well, 4 is not divisible by 3 and gives me an integer or a whole number for an answer. So, but I do need to break this apart then. I will break this apart into the cubed root of b cubed, because 3 is a multiple of 3, times the cubed root of b. And I have used the product rule again. 3 plus 1 gives me my 4 back underneath here. So now let's see how far we can simplify all of this. So it equals, the cube root of 8 is 2. The cube root of 3 stays as it is. A cubed stays as it is. We've already simplified that as far as we can. The cube root of b cubed is b. The cubed root of b stays as it is. So I'm just simplifying one factor at a time and writing it down. Now I need a final answer for that. So I'm going to put all of my rational numbers, ones that aren't under a radical sign, I will then place them together. So then my answer says that it will all equal 2a cubed b. Those are all the rational factors. They were a perfect cube answer. Times, now I use my product rule and I will put these two together. So I have the cubed root, and I multiply 3 times b of 3b. So I have my rational factors on the outside, my irrational times my irrational factor next. All right, that is what I have for examples. I'm sorry the video got over 10 minutes, but there's a lot of detail here in this one. Your assignments from page 435, numbers 31 to 49 odd and 51 to through 58 all. Please turn in after you finish and correct your answers. Let me know whatever I can help you with.